Okay, so we'd like to do an example of classifying critical points using the second derivative test. So let's quickly recall the second derivative test and the paradigm, and then go over an example. So we define the discriminant to be this value d here, and it's for critical points x naught, y naught, it's f sub x of x naught, y naught minus, or sorry, times f sub y x naught, y naught minus the mixed partial f sub xy at x naught, y naught squared. And so you calculate this value for every critical point you have, this discriminant, and then you come to the second derivative test, this page of cases here, and you see where your values fit. If your discriminant and the second derivative with respect to x are both positive, then f has a local minimum at this critical point. If the discriminant's positive, but the second derivative with respect to x twice is negative, then f has a local maximum at the critical point x naught, y naught. If the discriminant is negative, then f has a saddle point at the critical point. If d is 0, the test is inconclusive. And so the paradigm for classifying critical points is to first find all critical points, right? You find all points where f sub x, where the x partial derivative and the y partial derivative are equal to 0, or undefined, right? In particular, so I should say or undefined. It's a much more subtle and less reoccurring case, but it's still important to know that critical points can be where either of the partial derivatives are undefined. The next step is to calculate the discriminant for all of these critical points. And so you'll find the second derivative with respect to x twice, with respect to y twice, and then the mixed partial. And then you'll calculate these value for every critical point. And then you use all these values of the discriminant along with their second derivatives with respect to x at the critical point to apply the second derivative test. So let's see an example. Let's find and classify local extrema of f of xy equals 4x squared plus 9y squared plus 8x minus 36y plus 24. Okay, and so what is step one? Let's follow our paradigm here. Step one is to find the critical points. And so we need to calculate. Notice this is a polynomial, so there's no values we can plug in that will give something undefined. So f of x is 8x plus 8, and then f of y is 18y minus 36. And we set these equal to 0, and we solve this system right here. Well, thankfully, this is a very easy system to solve. And also, quickly checking 0, 0, right? If I plug in the point 0, 0, that's not a solution, so we're fine. But we always want to check the origin. And so we get immediately, kind of without not much algebra at all, we get that we have the critical point x equals -1, y equals 2, right? Because the solutions to the top equation is x equals -1, and the solution to the bottom equation is y equals -2. And so we only need to apply the second derivative test to one point in this problem. In the future, or in many other cases, you could have 2, 3, 4, etc. critical points, and you'd have to then apply the second derivative test each time. And so this was step one of our paradigm, to find the critical points, and we found that there was only one. What is step two? Step two is to calculate the discriminant for every critical point. Okay, well, we only have one, and so the discriminant is going to be f sub xx at the point -1, 2 times f sub y at the point -1, 2 minus f sub xy at the point -1, 2, and this whole thing is squared. So let's calculate some second derivatives here. F sub xx is going to be, well, it's the derivative of, so let me just copy the partial derivatives here. We have f sub x equals 8x plus 8, and then f sub y was 18x minus 36, or 18y minus 36, right? And so f sub xx is 8, and f sub y is 18, and then f sub xy is 0, right? Which is the same as f sub yx, right? If you take the partial derivative with either of these with respect to the other variable, right? Well, 8x plus 8 is constant with respect to y, so its partial derivative would be 0, and vice versa for f sub y. Now, these values for calculating the second derivative, or for calculating the discriminant, these are pretty nice because there are no variables in them, right? They're all just numbers, right? And so like immediately for f sub xx, we know that this is positive, right? And then also the discriminant is going to be 8 times 18 minus 0 squared. Well, I don't even care what 8 times 18 is. I know that this is greater than 0, right? All I need to know is that it's positive. And so this was step 2 to calculate the discriminant. In general, when you have more critical points and more difficult partial derivatives, sometimes your second order partials can still have variables in them. And when that's the case, that's when you plug in the point -1, 2 every time. And that's where you can get different values for different critical points, is because once the second partial derivatives still contain variables, well, then what point you plug in, it depends on what critical point you're calculating the discriminant for in that term. But we notice for this one, they're constant. And so it's kind of, we don't need to plug in the point. And so this was step 2, and we calculated the discriminant, and we got that it was positive. And we also learned that the second derivative with respect to x twice is also positive. And so step 3 of the paradigm is to apply the second derivative test. And we have a positive discriminant and a positive second derivative with respect to x. And so we come to the second derivative test, and we say, cool, case 1. Right? And so case 1 says that this is a local minimum. Step 3. So these two here imply that this is, that the point -1, 2 is a local minimum. Okay. And then usually you want to, for most applications, you want the actual like minimum or maximum value, right? If it's like profit or something, you want to know the maximum profit, not just where that occurs. You want to know what the actual maximum profit would be. And so usually what we'll do is calculate what the minimum value is. So what is f of -1, 2? Well, you just go back and plug it in here, right? And so for the sake of time, you can see, like, we know how to plug in -1 for x and 2 for y. So this is the minimum value of the function, right? Or it's a local minimum value, right? But anyway, so this was an example of using the second derivative test. Now, what I want to talk about next is open and closed sets, because here we can look at finding maxima and minima. If you remember, in the single variable case, when you wanted maxima and minima over a closed interval, we have the extreme value theorem that says a continuous function over a closed interval attains a global maximum and a global minimum, right? And so the candidates for these global maxima and global minima are critical points on the interior, like, or on the open interval, right? So there's critical points in here. These are contenders for the global max and global min, and so are the endpoints. So on closed sets, global extrema may occur at critical points of F or endpoints. And I want to say boundary points here. So the boundary of this interval is the two endpoints, right? So they may occur at the critical points of the function or boundary points of the domain, right? Because this is the domain here. Like in this example, the domain is the closed interval from A to B, right? And so how do we extend this notion to the multivariable setting? Well, let's look at open and closed sets first. So a closed set, I'll just start with closed. A closed set is a set that contains all of its limit points. Okay, and so what does this mean? This means if you have a set, so here's a closed set. Say I have a circle here, and I'm including the boundary of the circle, and I'm also including the disk on the inside. So my set, let's say my domain, this is my domain D. It's this disk that contains the boundary circle here. And what I mean by a limit point is you take any sequence of points that you can possibly construct, right? Obviously, there's a lot of them. So you define a sequence of points in your domain, and any possible limit of this sequence in a closed set is attainable, meaning the limit points belong to the set itself. Now, as an open set, imagine a disk without the boundary circle. So now we're just looking at like the interior of a disk with no boundary here, right? I could define a sequence of points inside of my set here that converge to a point on this exterior circle here. But in an open set, that doesn't necessarily belong to the set. Here's a limit point of a sequence in my set, but the limit point itself does not belong to the set. So if this was like the limit point, and here's some sequence, like S sub n, right? And so you have like S sub 1 is your first point, S sub 2 is your second point, S sub et cetera, and if you looked at like the limit as n goes to infinity of S sub n, and it's L, well, S sub n, the sequence belongs to the set, but the limit point may not, right? And this is an open set, is when you can have limit points that aren't necessarily in your set. Whereas a closed set, here, you can see if I include the boundary circle with this disk, well, then any sequence of points I take converging to points along the boundary, well, now here, my sequences are in the domain, and my limit points are as well, right? You can see here, so the example is like this would be a closed circle on the left, and this would be an open circle on the right. This is the idea of open and closed sets. And now what we have is, if we're looking over closed domains, we can get an extreme value theorem. Just like here, when we were looking at the closed interval, we have an extreme value theorem that says the maximum or minimum of the function must be attained somewhere in this closed interval. And it can happen at the critical points or at the boundary points. And we get this for closed sets as well. So here's the extreme value theorem. For functions of two variables, right? There is a generalization of this. So a continuous function say z equals f of xy on a closed and bounded set D attains an absolute maximum and absolute minimum at some points in D. So if our domain is closed and bounded, the extreme value theorem says that our function must attain a maximum and a minimum somewhere, must attain an absolute maximum or a global, right? Absolute can be synonymous with global in our vocabulary, right? And so what we have, and notice what the one of the hypotheses of the theorem is that our domain is closed and bounded. And so this is an example of closed and bounded. You can have, so a bounded set is something with boundary, right? Here you have boundary on like a disk. Like an unbounded set could be the entire plane, right? Like R2, just take the whole plane. This is closed and bounded. It's closed because it contains all of its limit points, and it's bounded because it has boundary. But the real two-dimensional space, R2, well, this is closed because it contains all of its limit points, right? You can have a limit converge to, or a limit diverge, or you wouldn't say diverge for a limit, but you can have limits that are infinity, right? But the real plane contains that. So they contain, the real plane contains all of its limit points. Take any sequence of points in two-dimensional space, take some converging sequence, and their limit points still live within the plane, but it's unbounded, right? There's no restriction on how far out I go. So this is closed and unbounded. And so what we're looking at is closed and bounded sets. So these are very nice sets, you know, like a domain of like a triangle or a rectangle or a circle or some shape, right? Closed and bounded are very nice sets in R2. And so the extreme value theorem says that functions whose domain, or if you're looking at a function over a closed and bounded domain, then it must attain a maximum and a minimum. And again, we've already discussed where global extrema may occur, And this is true for the multivariable setting as well. So I'll just come back here and kind of highlight it. And it's to say, where can the critical points occur? This could even be like a theorem. And let's say on closed, and now let's add the condition and bounded. So on closed and bounded sets, global extrema may occur at critical points or at boundary points in the domain. And so when you're looking at something that's closed and bounded, right? Like say we're looking over the circle. Inside, like the interior here, there can be critical points in the interior. And then you also need to check, is there any point on the boundary that could give us a global max or global min? And so that's what we'll need to check. We'll want to check critical points in the interior, right? And we will want to check the boundary. So let's see an example of how to do this. And these examples can be pretty lengthy. So example, let's determine absolute extrema of f sub xy equals x squared minus 2xy plus 4y squared minus 4x minus 2y plus 24 on the domain D, which is given by x and y, whoops. This is composed of the sets x, y, or composed of the points x, y in R2 such that x is between 0 and 4 and y is between 0 and 2. And so what is this domain, right? This is set notation here. And so this domain is points, so x is between 0 and 4, and y is between 0 and 2. And so this gives us a rectangle here, right? Because any point, including the boundary here, including the perimeter, any of these points is such that x is between 0 and 4 and y is between 0 and 2, right? And so you can see this is kind of, so this is our domain D. And we want to find the absolute max and absolute min of the function over this closed and bounded domain. How do we do that, right? So there's two possibilities, or there are two places we have to check. We have to check critical points on the interior, and we have to check the boundary, right? And so first, let's check critical points of interior. And when you're finding critical points of the interior, this is how we just find critical points normally, right? So take f sub x, set it to f sub y, set it to 0. And so we have f sub x is 2x minus 2y minus 4. F sub y is negative 2x plus 8y minus 2. Okay, so we can do our elimination technique, right? We're setting these both equal to 0. We can do our elimination technique where we subtract, or in this case, let's add the bottom to the top, right? And what does this give us? This gives us 0, and then it's going to be negative 2 plus 8, so plus 6y, and then negative 4 minus 2 is negative 6. So we have negative 6y minus 6 equals 0, which tells me that y equals 1. And if y equals 1, then that's 2x minus 6 equals 0, right? I'm looking back here. I'm plugging in y equals 1 to this equation. If I plug in y equals 1, then that tells me that x equals 3. And so we have a critical point at 3, 1. And so if you look here at the interior, you march 1, 2, 3 over, 1 up. So we have a critical point here. And this is one possibility for an absolute max or an absolute min. Okay. Notice we can check that again just by inspection. 0, 0 is not a critical point, so we're okay there. Now, what we want to do is start recording where our possible values or our possible values for extrema are. So let's box this so we can come back to it later. We have a critical point at the point 3, 1. And now we need to check points on the boundary. And this can become lengthy. How do you check points along the boundary? You parameterize boundary and then find max, or so let's find critical points of parameterized boundary. Right, so, or let's say parameterized function. Okay, and so let's see what I mean here. Our domain right now is the set of points x and y such that x is less or between 0 and 4 and y is between 0 and 2, and it gives us this this rectangle here. And you'll notice there are 4 line segments to the boundary of this domain, right? I'm calling L1 the bottom, L2 the right, L3 the top, and L4 the left. And we need to parameterize each line segment. So we need to parameterize each line segment. So let's do this for L1. All right, what is L1? If we're looking at L1, well, we may vary in x, right? If we're a particle living on this line segment L1, we may vary in x, but our y coordinate is fixed, right? No matter where we're at on L1, our y coordinate is 0. And so we can parameterize L1 by x of t equals t, and y of t equals 0 for t between 0 and 4. This is a parameterization of the line segment L1. Now, we need to find for L1, we need to find g of t, which is defined to be plugging in the parameterization to our function. And so once we've parameterized this piece of the boundary, we express the function along this boundary via the parameterization. And so the function is this long polynomial here. And if you plug in, remember, so x is t now, right? And y is 0. So plugging this in, if we look at g of t, well, x of t, or x is t, so we get t squared, and then y is 0. So that term vanishes, that term vanishes. And then we have minus 4t, the minus 2y vanishes, and then plus 24, right? And now, so that's what we got. We got that this was t squared minus 4t plus 24. We need to find critical points of the parameterized function along L1. So we want g prime of t, which is 2t minus 4. And then to find critical points, we set that equal to 0, right? And if you set this equal to 0, you get that t is 2. And when t is 2, you're at the point 2, 0. So this is another possibility. So here's a possible extrema, 2, 0. So let's box this as well. Okay, and so right now, thus far, we've found that a possible extrema is at the point 3,1, and another possible extrema is at the point 2,0. So here are the two possibilities so far. And now here's where these get lengthy. You have to parameterize the entire boundary, and you have to check the entire boundary. And you also have to check the corners, right? We haven't checked the corners, or we won't have checked the 4 corners. Sometimes they can show up in the parameterization, but rule of thumb, you'll want to check them always, no matter what. So let's do this for L2, right? L2, let me copy my domain here. And L2 was this line on the right here. And now, what do we have for L2? Now y can vary when we parameterize the line segment L2. Notice x is fixed at 4. And y can vary. And we'll let it vary just by the variable t. And then we're saying between 0 and 2. And so this is a parameterization for L2. And so let's call this one now, this function, when we parameterized L1, let me call that what we found g sub 1, right? And now we need to find g sub 2 of t, which is, again, f sub x of t, f of y of t, which is f of 4t. And if we plug this in, we get that g sub 2 of t is 4t squared minus 10t plus 24. Again, if you'd like, how I did this was you come back to the original function, which is this long polynomial here, and you plug in x equals 4, plug in x equals 4, y equals t. And if you'd like, you can pause the video and check that what you get is this. And so when we want to find the derivative, here we get 8t minus 10, which tells me that t is 5/4. And when t is 5/4, well, you come back up to the parameterization and plug in t. This is a possible extrema at the point 4, 5/4. So somewhere in here, 4, 5/4, maybe somewhere in here, there's a possible critical point. And so let's box this one. All right, and so we've got to keep going here. Let's go L3. Now we need to parameterize L3, which is the top line segment. And we want to parameterize this. Well, x is varying again, and y is fixed this time. But this time, y is fixed at 2, right? Like, we can move along L3, we can move however we want in the x direction, but our height is fixed, right? We're not changing y at all. It's always at 2. And so then we get g3 of t which is f of t comma 2, well, if you plug this in, what you'll get is t squared minus 8t plus 36. And so calculating the derivative here gives us 2t minus 8, which tells me that t is 4. And so we have a possible extrema at the point 4, 2. So here's another possibility, right? And we need to do this one more time. We need to do this for L4. And so L4, if you'll remember, on our box here, x is fixed at 0, and y is varying. And this is for t between 0 and 2. And so G4 of t is f of 0t, and you may calculate that you get 4t squared minus 2t plus 24. Okay, so the derivative comes out to be 8t minus 2, which gives me a t value of 1/4. And then coming back to the parameterization, that tells me I have a possible critical point at 0, 1/4. Okay, and then this covers all 4 line segments that make up the boundary of this domain. And I said we also need to check the 4 corners. So we also need to check 0, 0, 0, 2, 4, 0, and 4, 2, right? Those are the 4 corners of this domain here, right? Now, how do you check? You come up with all these possible values, and the last step is to check possible values. Biggest equals absolute max. The smallest is the absolute minimum. Okay, and so what do we do here? Well, let's gather this list of possible points. 3, 1 was a possible point. 2, 0 was a possible point. 4, 5/4 was a possible point. 4, 2 was a possible point, and then all these were, okay? And so to check, you need to plug all these in. So f of, we had 3, 1. We had 2, 0. We had, what else? We had 4, 5/4. Let me make sure I'm not missing anything. Yeah, and then we have 4, 2. Okay, and so notice we've accounted for one of the corners with the parameterization. Then after 4, 2, we had 0, 1/4 that we need to check. And then the rest of the corners. So 0, 0, 0, 2, and 4, 0. And so now what you'll have to do is these are all the possibilities. And so you'll have to come back to the function and you plug in all of these points to the function and you see what the values give. And so for the sake of time, I've plugged these in beforehand and I'll write down what you get for each one you plug in. So if you plug in 3, 1, you get 17. If you plug in 2, 0, you get 20. If you plug in 4, 5/4, you get 27.75. If you plug in 4, 2, you get 20. If you plug in 0, 1/4, you get 23.75. If you plug in 0, 0, you get 24. If you plug in 4, 0, you get, or whoops. If you plug in 0, 0, you get 24. If you plug in 4 or 0, 2, you get 36. And if you plug in 0 or 4, 0, you get 24. And now we compare you just look, you find the biggest, right? And so the biggest value I see is 36. This tells me absolute max at 0, 2. And this is why it's so important to check the corners, because this didn't show up in any of the parameterizations, but it ended up being the absolute maximum. And then so you can see we have an absolute minimum of 17, because if you look at all the numbers here, 17 is the lowest value. So this tells us that we have an absolute minimum at 3, 1. And this is how you classify, or this is how you find absolute extrema of multivariable functions or of surfaces. And so this could be pretty tricky. Or even if it's not too tricky, it's pretty lengthy, right? Especially when your boundary is composed of 4 line segments. You know, if you have a boundary that's composed of, say it's like a triangle, you know, something like, say this was your domain here. Well, then you only have 3 line segments to check, like L1, L2, L3. Or if it's like a circle, right, then for the boundary, all you have to do is like you parameterize the exterior or the boundary as, you know, so the boundary here, you could parameterize it as like g of t equals f of cosine theta sine, or how about t, sine t, right? Because that's how you parameterize the unit circle, is cosine t plus sine t, or like cosine t comma sine t, right? This gives you a parameterization for the unit circle. And so if you have a circle, a radius r, you can parameterize with like r cosine theta, r sine theta. But if you have something that's like a triangle or a rectangle, then you have to parameterize each line segment separately and then check all the boundary points. Okay, and so this is how this wraps up talking about finding absolute extrema on closed and bounded sets. And next, we're going to talk about Lagrange multipliers, which gives a way of finding maxima and minima under certain constraints. And there's some really nice theory about being able to calculate maxima and minima to given constraints. And that's where we'll go from here.